See, we have talked about a couple of two classification algorithms so far, and they all have their advantage, disadvantage. So that's why it's better we learn more algorithms. Also, because of the limitation of this class, 16 weeks, I cannot go too far. But I want to give you like a more of those most important concepts related to these algorithms. And in this decision tree, this one, it represents quite a few other algorithms like random forest and some other algorithm based on this. And this concept about Gini index, Gini impurity, and entropy, these are often used when you come to machine learning. So I included this lesson here. Also, we mentioned the K nearest neighbor. It doesn't suit when it has all those categorical features, and this decision tree is perfect when you have a data set with all categorical features, which you will see soon. Okay, so this is another very popular tool for classification, and at the end we will build a tree like this. You often see binary trees like this, right? For decisions. And this top node is called a root node, and all these nodes actually represent a feature. For example, it's called represents the age feature, and this one represents whether the person is married or not. It's going to be another column, another feature. And this one is actually the leaf node. Leaf node means that the decision has been made. It comes to the end. So these represent the classes of the target variable. So another concept is called a branch. This is a branch of this tree, and also sometimes you want to pruning the tree. If the tree is too big, that takes too computation power, or if it's not like if it doesn't align with the interpretability, then you also want to remove this tree as well. So that's called a pruning. Okay, so if we use the case, we use this case about cars, minivans, okay, we want to decide whether this person will buy minivan or not. We could use the features, the age as a feature. We could use whether the people are married or not. If there's a column called married or not, we could use that feature, right? They are different features in there, all those data sets. Then the first thing we have to decide is which feature we put on the top. For these decision trees, you see, what we really need to decide is what the structure of the tree, which feature on the top, and then after that feature goes what feature goes next. Right? That's how do we decide which feature is the best feature to classify the data. So it comes to this concept called Gini impurity. For example, here, for this data set about buying minivan, or not. If I have a feature called whether this person column called family, okay, whether this one has a family or not, okay, usually no. If the person has a family, okay, all of them will buy everybody here will buy minivan. Okay. If it doesn't have a family, okay, everybody here has no non-minivan. Okay, and I just use A. And another feature called age. Age. This doesn't classify very well. This age larger than 30. After using this feature, larger than 30 and younger than 30, okay, some have minivan and some doesn't have minivan. And here also younger than 30, okay, probably less people, fewer people have minivan, and more people have no minivan, no minivan. Okay, so which feature will be better?
The family one.
Family one, because clearly classified this data is set into two groups. So we would choose this feature, right? So this is the concept called junior impurity. This one, the impurity is impurity. It's the opposite of purity. Okay, so this one is impurity. This is a perfect purity, right? The impurity goes to the lowest, 0. Okay, and then this is the best feature. The impurity is well, the purity is high. The impurity is the lowest, 0. Then this is the best feature. And here it's mixed. Okay, it's not a good feature. This number probably between 0 to 0.5. Why is it 0.5? Because the equation for junior impurity is this one. 1 minus the probability square. Okay, the probability square altogether. For example, here, if it's a half-half, for example, it's half-half. Okay, two people buy minivan and 2 people don't buy minivan. This is half-half. Then the junior impurity will be 1 minus this one, right? 1 second, right? That's the probability. 2 divided by 4, that's the probability. The square, and the plus this probability is also 1 second half. So, and altogether that's 0.5. So that's the maximum number of junior impurity. Half-half. That's the worst feature. Any question here so far? So this number doesn't go from 0 to 1. It goes from 0 to 0.5. That's the maximum number of junior impurity, 0.5. See. All other numbers will be smaller than this one. For example, if it goes males are 1 and female, minivan are 1 and non-minivan is 3, then this number will go 1/4 square plus 3/4 square. See, this one must be, this result must be larger than 0.5. Smaller than 0.5. 16th 10, so it will be 16th 6. You see, it's smaller than this one. Now, half-half is the worst case. The worst impurity. Okay, we can look at another example. can look at this example, okay? How can we calculate the gene impurity? So this example, we have a data set and the target variable is that we want to find the people who will buy ice or not. Okay, there are 3 cases bought ice and 4 cases didn't bought ice. And so we want to find the first root node, right? First feature for our tree. Then let's try the popcorn and the soda and to see which one is a better feature to classify this class. So if we go with the okay, if we go with popcorn at the beginning, yes or no. At the beginning of this, before we divide by popcorn, what is the probability here? The probability is how many buy ice, how many buy no ice? Yes and no. That's 3 to 4, right? 3 buy ice and 4 didn't buy ice. After we divide by yes, divided by love popcorn, how many buy ice, how many didn't? For those who loves popcorn, how many buy ice, how many didn't? See, these are the cases love popcorn, right? These are the cases who loves popcorn. So in this group of who loves popcorn, how many said yes, how many said no? Yes is 1, right? This one. That's the only case in people who love popcorn, the popcorn, okay? Popcorn. So here this is the root node. We chose popcorn. And for those who love popcorn, there are 2 no, and here this group is also love popcorn, right? How many yes, how many no? 1 yes and 3 no here, right? So the probability, the ratio is 1 to 3, right? And the probability of loving popcorn, no, the probability of buying ice is here, this node. The probability of buying ice is what is probability of buying ice? Here. 1 person buy ice, 3 person that didn't buy ice. So the probability people buy ice at this node is 1 to 3 is the ratio, the probability is 1 divided by no, 3 said no, 1 said yes. So the probability the people will buy ice is
Like 0.3333.
Guess for the percentage or?
percentage probability. So in a class, there are 3 male, 1 female. What is the probability that, yeah, 1/4, yeah, 1/4. That's right, 1/4. And then the probability of not buying is 3/4. And the junior impurity equation is 1 minus the square of the probability. So this one is 1 minus the square, the probability of the square, right? So this junior impurity is 16.6, right? And then you have to calculate the, because it has the 2 nodes here, 2 nodes here. So this one we calculated, and then you can have to calculate this one as well. So for people who doesn't love popcorn, how many buy ice? 2 buy ice, and then 1 didn't buy ice. So the ratio is 2 to 1, and then the junior impurity is 1 minus same. You tell me.
2/3.
2/3 square plus 1/3 square, and this one is 9/5, 9/4, and then so we are calculating the impurity of this whole group, right? After dividing by popcorn. So this whole level, the impurity is you have to divide by you have to time the ratio. So here is 4 people, and here is 3 people. So this is 7/4. So you have to do 7/4 times this impurity number, right? 6 plus the impurity is this one is 7/3. So 7/3, the weight of this side is 7/3, and then the impurity number is 2/4. So after getting this is the number we get. If we use a popcorn as a feature, as the first root, right?
Where'd you get the 3/7 from? And the 4/7? Just how many people are left over, or? And the one where you have the 4 fractions multiplied by each other. I see the
Yeah.
6/16 from the 4/9, but where do you get the 3/7 and 4/7 out?
4/7 is 4 people here, 7 people, 3 people here. So this is the weight of this one.
That's just the total people.
Total people, yes, 7 people, yeah. I want to calculate this. How can I do the calculation? I'll need a calculator. Let's try this, the other one. If we do the if we use love soda as the root node, what will be the junior impurity you get? Try that on your paper. Don't look at my answer. You try it on your paper, okay?
We're doing the ones who buy ice that love soda, or
By ice is the target. So we are using soda as the root node to classify it. Oh, you can calculate this one. Purity. We are working on this. Good. Yeah. Good. Okay. So which one is smaller? Which one is bigger? Yeah. Which one is bigger? Which one is smaller? Soda. What you got?
so the one we just did before, or
Compared to this one, yeah. Yeah. So let's see. Okay, what we got. Soda. So there are 4 people love soda and 3 people don't love soda. And if for those people who love soda, 3 choose yes and 1 choose no. So the Gini impurity of this node is this node is 3 divided by 4. That's a probability, right? The probability, and then plus 1 divided by 4, and you have the square and the sum. The result of this one is 16, 16th of 6 of 16th. And then this one, for those who don't love soda, they all said no to buy ice. So it's 3-0. If it's 3-0, it's a completely purity. So the impurity is 0. You don't have to calculate this. That's why I write 0 here. And this is a 16, 6. And then you times the ratio of this branch is a fourth, and for this branch is a 3. So this ratio is a fourth divided by 7. You times this one, right? This you times this impurity. So the final result we got of the Ginian impurity of this one is 16.6 times 7/4. So which one is it's compared to this one?
Are we supposed to multiply them out to get the decimal for it, or just leave it in fractions?
Here we can leave the fraction. See, we are comparing this one to this result. Obviously, you can see which is more pure. Which one is more pure here?
The other one.
This one or this one?
The other one has to be-
The other one. Because this first part is the same actually. It's all 16.6 times 7/4. But the second branch is 3 to 0. This one is very pure. Right? So this impurity is lower. See? The result of this one, the second part has a number, and the result of this one, the second part is 0. It's pure. So this one is lower, and this root node, love soda, is better than the first one, love popcorn. We all good here? John, you good? Is the result the same?
I'll just need to work through some more of these.
Okay.
Can you go back to the last?
Well,
Can you go back to the other slide?
yeah.
Final price. Yeah.
Yeah. So here comes a third column I didn't use. That's the age. Age. How do you do the root node of age? Because the popcorn is a categorical. Okay, I just have to branch yes, no, and the age. Obviously, you cannot easily say yes, no. How do we do that? So if it's a numerical feature, what we do is usually first is a sort from smallest to largest. For example, it goes 7. This is sorted. Okay, this is sorted. Yeah. So sort, and then you get to the numbers. Get to the numbers of. I believe it's the mean of these numbers. Like this is probably 9. The mean of this is 9. 9.5 might be used 9. And this mean is 15. And then you try different node. Like try age small 9 as the dividing point, and then you get to the Ginian impurity, right? And then you try age like 15, and then you get an Ginian impurity value as well. It's the same calculation method like what we did. And then you compare which one could better classify this data, and then you choose this one. Okay. If this Ginian impurity is smaller, okay, the algorithm will choose 15 instead of 9 for the age. For the age, that column. So you can see that the computation behind it is quite costly. But this is the first metric of deciding the node for the division tree. there's a second metric that is used called entropy. Entropy, it's similar to genuine impurity, and you will see that the result is usually the same, but the concept is a little bit different. It doesn't measure impurity. It's called, it measures the unpredictability. Unpredictability, okay, it's quite hard for me to pronounce that. What does that mean? So, for example, if you have a result, okay, all males, then the unpredictability of this one is 0, because you can easily predict it. Okay, everyone I pull up is a male, right? If you have a node and then divide the data into male and the female, and then this unpredictability is 0, because everybody you pull up is male. Okay, and if it has a half male, half female, okay, the unpredictability goes the highest one, because you're not sure. It could be male, could be female. That's 50% to 50%, and then this entropy goes to 1. That's called it. That's the concept about entropy. At the beginning, you will have all kinds of animals, and the entropy is high. And at the end, you classify them into different classes. So there's the 0 entropy, because the unpredictability is 0. You can easily predict this group. Okay, everybody John from this group is a giraffe. So it goes from if you have the decision tree, the entropy goes from high to lower, or to 0. Sometimes you cannot reach 0. Okay, not every decision tree, not the leaf node of the decision tree, not every tree is pure. So the goal is the same, but the metric, the equation is a little bit different. You see the equation, okay. So the formula is a little bit different. Instead of using that square, 1 minus the square sum of the square probability. So this one, this is the formula for calculating entropy. Right? We can try this again. All right. If we split by soda. See, if we split by soda, this one, the entropy of this one will be entropy of this one. Is obviously I don't like to calculate the log also, so it's 1. I'll do the third first. Okay, 1/3, and then log 2 this one, and then minus 1/4 log 2 1/4. Okay, that's the entropy of this node. And then the entropy of this one is if it's 0, 3 to 0, then it's 3 to 0. Should be easy, right? Entropy should be 0. Entropy should be 0. Okay, so this is the final entropy if you use soda as a root node. And if we use popcorn as the root node, we use the popcorn as root node, then the entropy is 1/4 log 2. It's actually the same, exactly the same, you see. Times the log 4. And then the entropy of this one, it has a value, obviously. So it's still, so the entropy of this one, it's the same as the other, but when we choose soda, and then the entropy of this node, it has a number, so still the love soda is a better feature to classify it. So you can see that the result will be almost the same. Usually it's the same result. Okay, I'll leave you to calculate this, and if you don't fully understand, there's also an additional video to explain this concept. But usually, the Gini impurity and the entropy, the values, they are the same. So for example, here, when the probability is 0, then this impurity and the entropy value are 0. And when it's half, the Gini impurity value is 0.5, and the entropy is 1. If it's half, you can see the probability, half and log 2 half, right? What's the result? It's -1. So this is also -1. So added together is 1. So entropy, when entropy is 1, the Gini impurity value is 0.5. And if you use this line and times 2, you can see these two lines. It's look almost the exact same. So these are two metrics, but usually result in the same result, same thing.
Is that how it usually works? Is your Gini usually double? I mean, your entropy usually double your Gini?
Oh, yes, usually like double.
So if you get like the final result of your entropy, could you just divide that by 2 and that would be your?
Not divided by 2. No. In equation, everything, if you divide by 2, everything by 2, it doesn't affect the result, so we don't do that. Yeah, but if you divide the entropy's result by 2, it should be close to the Gini impurity value. This map just, this chart just shows that. But we usually use either one. Entropy probably uses more computation power because it has the log. All right, let's walk over this example. This is a data set. Read this data set about whether you should give the people the loan or not. Okay, so this one. There are a lot of data competitions on Kaggle, and they all publish the code. So after this class, if you want to further learn, you can read those reports, learn from those reports, and then you can try to go to this competition. That will be very helpful for your growing. Okay. So. See this data set, and it has each person's application, whether they have dependent, what is their education status, and then the target variable is whether the loan is approved or not. Okay. Loan term, loan amount, and income categorical loan amount, and it's long term. This long term is actually could be categorical or it could be numerical. Credit history 10 numerical, categorical. So most of the features are categorical. Okay, now let's start to load this data set. Here's my Google Colab. See, if you don't have like Python on your desktop, you could use Google Colab. Sometimes I use it. It's the training, so I need the training data. Then I'll be able to read it, and this is just a general data processing. Right? I really want to show you is the end. Why it doesn't let me copy? It doesn't let me copy.
Would edit on the toolbar, would that let you paste?
Well,
Right under Untitled
This one?
4, where it says edit, would that have the paste option? It's not.
I did use Control V. It doesn't let me copy. Well, all right, then I started on the corner. So just check whether it's balanced or not. Alternatively, you can use histogram. I think I prefer histogram because it's that you have a better visual. And then here, here you could do. There are two columns called applicant income and co-applicant income. You could leave them as it is, or you could do, because based on my experience, usually they base on what they do is to calculate both like the co-applicant and the main applicant, both of their income considered. That's why I put them together. But you could leave them as separate. As when we do the data training, build a model, oftentimes you have to build upon your experience. Even with the result, you have to check whether the model is interpretable or not. For example, we said, yeah, maybe you are predicting whether people will have stroke or not, and then the model you got, the final model you got, it has the feature how much money the person have. This could be related, but that will affect the interpretability of your model. Right? It's not a direct factor. Then you could modify your model to remove that feature. Right? So. And oftentimes when you work on the features, like we have to remove features or we have to edit the features, and also it has to based on your experience. I'll just do this numerical value transformation. Here, long idea we now use, but dependent, it's object, so need to change it to numerical. And then next one, yeah, you do the testing, training, split, and then the balancing. Okay, quickly do that. What was the new code for that? Forgot.
Example,
Oh, yes.
or I think it might be fit example. I'm not really sure.
Fit resample. This one? Not fit resample. Should be fit resample. Resample, you should be correct. Okay, it's another error actually. Cannot convert a string to float. Didn't drop the ID. Didn't drop the ID. ID. Okay. Next is here. Next we build the tree. Okay. This should be enough. I don't think we need this line. Here, as you see, my slide, the default algorithm uses linear impurity. However, you can change the criteria to entropy. Okay, and the max depth is sometimes when your data is very big, is huge, and then the features are you have lots of features, then it cannot come to the perfect status, like every class is classified. Like the picture we have here, every class is classified, right? It has at the end of the tree, each leaf only has one class. That comes to the perfect result. However, sometimes with your data set, it cannot come to the perfect result. So what you need to do is to specify the max depth of the tree. If it's 3, then it has 3 levels. Okay, it will stop classifying after 3. And if it is 4, of course, the tree will go deeper. Usually, if how do we decide this number? Same like k-nearest neighbor, you try different number and see which one gives you the best accuracy of the model. Which one the model gives you best accuracy. If the depth is 3 and the other model depth is 4, they give you the same accuracy, then which one we should choose? Which choose the 3, because we prefer models that are simpler. They have they use less computation power, and it's easy to understand. Right? We always choose the simpler model if they give you the same result. Here in this model, we choose the depth as 3, and then we use this model to fit the data x, y, and then you will get the result. Okay, so just copy the code. So the accuracy we got is the 0.84. That's pretty good. What I really want to show you is that at the end, you will get a tree like this. So you could use this library graph visualization, and then you can visualize this tree. This tree, yeah. So tree, you can export this picture of the decision tree. You tell it the model you built, and then the features, the feature names, and whether you want to show the class name or not. You can try these different. You can try different arguments to see what the result will be. Okay. So here, build this tree, and then feature names. Class name is true, and the source is the dot data. That's why you just use this code, and the render is a Gini because we used the Gini impurity here for this algorithm. So if you don't specify this, what you will got is a tree doesn't have name again. What's going on here? No module. Okay, I have to install this library. I include that tree here. I didn't. So as we see this method, is this algorithm, it's very easy to understand, and it does handle missing values. So even our data set has a lot of missing values, you don't have to address them. And adequate. And the disadvantage of this algorithm is that I may result in overfitting. if your tree is too big, it may like result in overfitting and it may use too much computation power of when you have a lot of feature in a large data set. Okay? And it's very good for categorical features. If you have all categorical features, this is a good option. And also, yeah, it need balancing the data before you use it. But overall, this decision tree, it's a simpler algorithm. Imagine if your feature has a different has a numerical columns and they are all on different scale. Do we need to balance it? Or do we need to scaling it? For the decision tree, you don't have to put them in the same scale, right? Because it's just based on the impurity calculation of the impurity. It's not based on the distance. So you can skip some of those steps. Oh. Oh no. So, probably need to restart this. I have to restart the whole still tells me no module. So may have to like restart the computer for it to be effective, I believe. Don't know why it still doesn't work. Yeah, it should work. I did install it. Yeah, if everything doesn't work, you just need to restart the computer. Probably will work. Or you have to check in the terminal to see if this library is installed or not. It still tells me no library. Okay, I guess I cannot solve it here in this class, so you can try this code by yourself, okay, and to see how this tree look like. Eventually, what you got is a tree with all these features, whether they have adaptation or not, and you will see that the tree at the end of the tree, all the leaves, they are not pure classes. Each leaf will have a combination of people had a loan approved, but their loan is approved and not approved. So it's not, it doesn't come to the perfect result we showed in these pictures. In these pictures, we showed the perfect result, but in reality, the result is not perfect. Yeah, at each leaf, there's the giraffe and that other animals. Each not. Okay, I'll leave this for you to try after this class. Okay. All right, then we'll see you on Thursday, next Thursday. Tuesday, I have some other conference.
Okay.
I no class on Tuesday. So we have the lunch and the learn on Thursday.
Um. What's wrong? Question you have is set this one built so I want to here. So we normalized it in the last one. And it says I'm gonna build it. So I want to copy it. Yeah, just set it up. And when I run it every single time I run it, I get the same error, which is unknown label type.
Unknown label type. Go back and you run into the same problem. Print out some X. Can I see some of the X? This is the X you printed out.
This is just for just two values, but you said use all of them, so this is the X's that got printed out. But I don't see any non-numerical values, so I'm not sure why it's doing that. So they're all ones and zeros.
See if but I don't want to. Not there.
Yeah, something. So I use the Y value. Y value is our target. Sure. So that's also numerical. Just when I printed the it showed just ones and zeros for the values, it didn't show any other values.
Why?
Y is gonna be the target value, so that's gonna be a computer. So. So this is something that you should go to get a little more. It'll show you. Yes. Okay, so when I scroll back up, when you do the null test, it so I print yeah, and it prints everything where it's 1 0 1 0 1 0. So it's all ones and zeros. But when I test for empty values in the same exact value, it shows that shows nulls. So I don't understand how when I print yeah, it shows 1 and 0, but when I check for null values, it does everything's null. Not entirely sure how or why that works. I don't think it because it doesn't want now, it's just me testing it, so when you run it, I won't be there anymore. But that's the diagnosis result.
Yeah, yeah, 3000 that Y. Y. 3000 Y of value constantly there might be. We'll show you what the abnormal state is out.
Y dot value counts.
Yeah, do that value accounts on the Y.